Welcome to the Explainer. Today we're going to unpack this massive, totally invisible engine that is literally running all around us all the time, the Earth's atmosphere. We're going to look closely at the precise mechanics of weather, specifically how heat travels, how it behaves, and ultimately how it directly impacts the entire world of aviation. We've got a really fascinating journey ahead of us today, going all the way from the burning surface of the sun right down to the tarmac of your local airport.
Now, to really ground our journey today, I want you to picture this. Why is it that airplanes need significantly more runway to take off on a blazing hot summer afternoon compared to a crisp, freezing winter morning? I mean, it's the exact same airplane, right? Same engines, same stretch of pavement. But the physics of getting that metal bird into the sky, they change drastically based entirely on these invisible meteorological factors. Today, we're going to solve this cause and effect mystery together, step by step.
All right, let's start with Section 1, measuring the heat.
So at its core, temperature is really just the degree of hotness or coldness of a body. And while aviation relies pretty heavily on the standard Celsius, Fahrenheit, and scientific Kelvin scales, actually capturing these metrics, well, it's not quite as simple as just checking a thermometer on your back porch. To figure out what the air is doing miles above our heads, meteorologists have to send up these specialized instruments called radiosondes. They basically strap them to weather balloons and launch them high up into the atmosphere.
And down on the ground, getting an accurate measurement is equally strict. You can't just leave a thermometer out in the blazing sun and expect to get an accurate read of the air around you. It just doesn't work. Instead, thermometers are kept inside this brilliantly designed louvered white box. It's called the Stephenson screen. And it always sits exactly 1.25 meters, so about 4.1 feet above ground level. But here's the really crucial part. The door of that Stephenson screen absolutely must open opposite to the sun. This ensures direct solar radiation never hits the thermometer inside and messes up the data when a meteorologist opens it up to take a reading.
Moving right along to Section 2, incoming solar radiation.
Okay, let's dive into this, because we really need to clear up a major meteorological misconception right off the bat. We feel the sun's warmth on our skin, so it's completely natural to assume it just directly heats the air around us, right? Well, actually, no. Incoming shortwave radiation from the sun is mostly infrared and visible light, along with a tiny touch of ultraviolet rays. And because these wavelengths are just so incredibly short, they literally pass right through our atmosphere almost without heating the air at all. Crazy, right?
So you're probably wondering, where on Earth does the heat actually come from then? Well, those short waves from the sun eventually strike the surface of the Earth. And this process, where the Earth's surface gets heated by incoming solar radiation, is called insolation. But here's the catch. Not all of that radiation gets absorbed. The Earth has a reflecting power, which scientists call albedo, and different surfaces reflect totally different amounts of energy. For example, think about a pure white blanket of snow. It has a massive 80% reflecting power. That means it bounces 80% of that solar radiation right back out into space, which is exactly why the ground stays so incredibly cold.
Which brings us to Section 3, how the atmosphere heats.
And this brilliantly illustrates exactly what's happening. Think of a pot of water boiling over a campfire. First, the Earth absorbs the sun's energy and then radiates it back out as long-wave terrestrial radiation. And that long-wave energy is what actually heats the atmosphere. Second, we have conduction. This is heating by direct surface contact. So the air lying right smack against the hot Earth gets heated by contact, exactly like the handle of a metal pot getting hot. But air has pretty terrible conductivity, so this really only heats that very bottom layer. And finally, we have convection. As that bottom layer of air heats up by conduction, it expands, becomes less dense, and it rises. These upward currents, or thermals, carry the warm air up into the higher atmosphere, exactly like the rolling, boiling water rising in our pot.
Now, it's really important to distinguish between how heat moves vertically versus horizontally. Like we just talked about, conduction is the direct transfer of heat to the air actually touching the ground, which then rises. But weather is also driven by something called advection. Advection is simply the horizontal movement of air. So when you feel a hot, dry wind suddenly blowing across a plain from some neighboring desert, you're experiencing advection. It's basically massive blocks of air carrying their temperature characteristics sideways across the map.
But okay, get ready for a truly mind-blowing fact about how our atmosphere gets its heat. While radiation, conduction, and convection are all super important, they aren't even the biggest players here. Get this, 77% of atmospheric heat actually comes from the process of condensation.
No way, right? It's true. As air is lifted, it cools down and all that invisible water vapor floating in the air condenses into visible cloud droplets. And when this phase change happens, it releases an absolutely massive amount of what's called latent heat directly into the surrounding atmosphere. So yeah, over 3/4 of all atmospheric heat literally comes from clouds being born. Just incredible.
Let's move to Section 4, the daily temperature cycle.
So if I were to ask you right now when the hottest part of the day is, you'd probably guess noon, right? I mean, it makes complete sense. That's when the sun is directly overhead at its absolute highest peak. But surprisingly, the actual highest temperature of the day consistently hits around 1400 hours, or 2 p.m. So why is that? Well, it all boils down to a solar lag effect between incoming and outgoing energy. Even though the sun starts getting lower in the sky after noon, for the next 2 to 3 hours, the Earth is still taking in more incoming solar radiation than it's giving up as outgoing terrestrial radiation. Think of it kind of like your bank account. As long as your incoming deposits are bigger than your outgoing withdrawals, your balance, or in this case the temperature, is just going to keep going up. It's really only around 1400 that the outgoing radiation finally overtakes the incoming, and that's when the temperature actually starts to drop.
Now, what's really interesting about this slide is how cloud cover completely alters this daily cycle. During the day, clouds basically act like a giant shield, reflecting the sun's shortwave radiation away and keeping the surface a lot cooler. But at night, they act like a thick blanket. See, the Earth cools off by emitting long-wave nocturnal cooling, but clouds trap that warm air right between their base and the surface, completely preventing it from escaping out into the upper atmosphere. And that is exactly why cloudy nights always feel noticeably warmer than those clear, star-filled nights.
So, just to summarize this whole daily timeline for us, the sun hits its absolute peak at noon. The temperature peaks a bit later at 1400 hours, and then it falls continuously all through the night. And actually, the absolute lowest temperature of the entire day happens about 30 minutes after sunrise. That's right before the new incoming solar radiation is finally strong enough to counter that ongoing nocturnal cooling. Oh, and it's definitely worth noting that this daily temperature swing, what meteorologists call the diurnal variation, is way greater over land than it is over oceans. Land has a very low specific heat, which basically means it takes very little energy to heat it up super fast and it cools off just as fast.
Which brings us full circle to Section 5, air density and performance. Okay, so density is simply the mass of air contained in a given volume. When it comes to flying an airplane, you want thick, dense air. The engines absolutely need dense air to burn fuel efficiently, and the wings need it to generate lift. But there are quite a few things that lower air density. Lower pressure naturally lowers density. Moist, humid air is actually less dense than dry air, which usually surprises people. And higher altitude lowers density dramatically. To put that into perspective, at 6 kilometers, or about 20,000 feet, air density is practically cut in half. But for day-to-day operations, the most dynamic factor is heat. The warmer the air, the more it expands, and the lower that density drops.
So the crucial point is really what we're looking at here. Down at sea level on a normal, cool day, the air is thick and dense. The airplane's engines are producing maximum thrust, the wings grab onto that air easily, and the plane lifts off after a relatively short run. But switch that up to hot and high conditions, like a scorching 14-hour summer afternoon, and suddenly that air is thin and expanded. The engines are literally starved for dense oxygen, the wings have way less air mass to push against, and the aircraft physically cannot climb as steeply or as quickly.
And this brings us directly to the ultimate meteorological rule of thumb in aviation. Higher temperature means a longer runway is required for takeoff. Boom. That perfectly solves our initial mystery, doesn't it? On a freezing winter morning, the air is packed super tightly together, offering incredible performance. But on a hot summer afternoon, the terrestrial radiation has heated the surface through conduction, convection has pushed that warm expanded air upward, and the resulting low density forces the pilot to use significantly more of the runway just to build up enough speed to force those wings up into the sky. We've seen how heat fundamentally stretches the air and challenges an aircraft. But I want to leave you with one final thought to ponder. We just learned that moist air actually has a lower density than dry air. So if high temperatures stretch out your takeoff roll, how would a hot and deeply humid tropical afternoon further compound the physics? How exactly does water vapor secretly rewrite an aircraft's takeoff math? It really just goes to show that in the atmosphere, every single element interacts, creating this endlessly fascinating puzzle. Anyway, thanks so much for joining me on this explainer. Keep your eyes on the skies and never stop questioning the invisible forces around us.